Okay, so hello everyone. So this is the problem solving season for week 4 of the course Introduction to Rings and Fields, and I am Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. Okay, so let's recall the topics which have been taught in the week 4. Then I will solve some problems based on those topics. So in week 4, we have saw that every ring has maximal ideal. So we have saw existence of maximal ideals in ring. So note that all our rings are commutative ring with identities and which are non-zero. Then we have saw Chinese remainder theorem. And after that we have saw what do we mean by irreducible polynomials or irreducible elements. So using this, we have characterized maximal ideals in a polynomial ring over a field. And after this, we have saw field of fractions of integral domains. And we also have saw a couple of examples of field of fractions. Then we have saw one important class of rings known as Noetherian rings. And in the end, we have saw one celebrated theorem known as Hilbert basis theorem. So we will be solving problems in these topics only. So let me put that assumption that all our rings are non-zero rings. So ring means commutative ring with one, and that one should be non-zero. So that means all our rings are non-zero rings. So we will assume this condition throughout the course. Okay. So let's recall that we have saw that if R is a ring, then R has a maximal ideal, right? Every ring has maximal ideals. Now let's see some consequence of this result. So first of all, okay, so prove the following statements. So first of all, uh, first statement is every ring has a prime ideal. And second, if R is a ring and let's say X belongs to R is a non-unit, then X is contained in a maximal ideal. So these are very trivial consequence of this earlier statement. So let write down the proofs formally. So first one is every ring has prime ideal. So we know that every ring is maximal ideal and every maximal ideal is prime ideal. So from that this follows immediately. So since every ring has maximal ideal and maximal ideals are prime ideals. So we have nothing to prove in this case. So maximal ideals are prime ideals, the result follows immediately. Okay, now part B. So part B says if you take a ring R and take a non-unit, means which is not an invertible element, then that element must be contained in a maximal ideal. Okay, so let's try to prove this. So let R be a ring and X belongs to R be a non-unit element. So consider the ideal, let's say I, which is generated by that non-unit X. Now since X is a non-unit element, so ideal generated by X cannot be the whole ring. So that means I is a proper ideal of R because X is non-unit. Now R is a proper, sorry, I is a proper ideal. So that means R mod I is a ring and it is non-zero. So that means R mod I has a maximal element, maximal ideal. Okay, and by correspondence theorem we know that every ideal of this quotient it is looks like J mod I, where J is an ideal which contains I. So maximal ideal, let's say M mod I. So then M is a maximal ideal containing I. So that means M contains ideal generated by X. So X must belongs to M. So this result is also easy to prove. From the first part, we can also conclude that every non-unit is contained in a prime ideal. Uh, okay. So in the first part, we have used that every maximal ideal is prime, but we know that the converse need not be true, right? So prime ideals need not be maximal ideals. But there are some rings in which this practice. Okay, so let's see the next problem. So let R be a finite ring, then prove that every prime ideal in R is a maximal ideal. So if a ring consists of only finitely many elements, then every prime ideal in that ring must be maximal. Okay, uh, let's see the proof. So recall that an ideal I is prime if and only if the quotient R mod I is an integral domain, right? So if and only if the quotient is an integral domain. So that is something we have already uh, saw in the lectures. So we will use this fact. So so we need to prove every prime ideal is maximal. So let's take a prime ideal. So let P be a prime ideal of R, right? So that means if and only if R mod P is an integral domain. Now it is given that R is a finite ring. So R consists of finitely many elements. So its quotient, it is also a finite set. So that means uh, R mod P is a finite integral domain. Since R is finite. And in the lectures, we have saw that every finite integral domain is a field. So if you cannot recall, you can go back to the lectures and see. So that means R mod P is a field. And this quotient ring is a field if and only if that ideal is maximal. So if and only if P is a maximal ideal. So we have taken an arbitrary prime ideal and we have proved that it is a maximal ideal. So from this we can conclude that in a finite ring every prime ideal is maximal. So this is a very trivial stuff. Okay, so do you have any doubt in this or in the previous problem? Okay, so then let's move on to next problem. So next one is true or false. So you have to determine which one is true and which one is false, or the otherwise. So the first statement is, okay, let me write which of the following statements are true. Okay, so the first statement is, you take this quotient ring Rx mod ideal generated by x square, and this says it is isomorphic to Rx mod x square plus 1. And second one is Rx mod x square is isomorphic to Rx mod x square minus 1. And the third one is Cx mod x square plus 1 is isomorphic with Cx mod x square minus 1. So we have three statements. In the first one, we have this isomorphism Rx mod x square is isomorphic to Rx mod x square plus 1. In the third one, Rx mod x square is isomorphic with Rx mod x square minus 1. And in the last one, Cx mod x square plus 1 is isomorphic to Cx mod x square minus 1. So you need to check which one is true, or which, there can be more than one statement true or false. So you have to determine that. So try to think it for a few minutes. So first try to see the first problem. So, is this an isomorphism? Assignment 3 problem. So assignment 3 is the deadline over, then only I can try to explain it. Okay, so assignment 3 problem 1 option 3. Okay, so I don't recall. So let's solve this problem first, then we will come to that assignment problem. So try the first one. So is this an isomorphism? First one should be easy. So I hope you have saw this ring in the lectures. Can you identify this ring with something known? Okay, so let's do the first one. So, I hope you can recall that this ring, it is isomorphic to the complex number. It is isomorphic to C. So Rx mod x square plus 1 is isomorphic to C. I think this thing has been done in the lectures. So this is by just if you take this map from Rx to C, where f of px maps to p of I, then you can see that this isomorphism using this homomorphism. So you try to prove this. So that means this quotient is a field because C is a field. So Rx mod x square plus 1 is a field. But is this a field? What do you think? So to check it is a field or not, you need to check this ideal is maximal or not. So this ideal, even it is not a prime ideal, right? So you can see it, x square is okay. So let me write, but x square is not a prime ideal. So Rx mod x square cannot be a field because this is not a prime ideal, so this cannot be a maximal ideal, so the quotient cannot be a field. So this is not a prime ideal. Can you see why? Because x square belongs to this ideal x square, so that means x times x belongs to x square, but x does not belongs to x square. Or you can directly see that this is not an integral domain because x mod x square, this element is a zero divisor because its square you will get zero. So first one is false. So these two cannot be isomorphic. Okay, if you understand this one, try to prove the second thing. It is isomorphism or not. So here you will need the correspondence theorem. Did you understand the first one? Yeah, okay. Try to do the second one. You can use the correspondence theorem. So from that it will be easily followed. Or you can also use the let's say Chinese remainder theorem. Okay, let me do it using the Chinese remainder theorem. So I will use the Chinese remainder theorem to prove that this ring is isomorphic to a ring, something known ring, or something which is easier to handle. So here is your ring Rx mod x square minus 1. Now x square minus 1, this ideal is basically product of x plus 1 and x minus 1. So this polynomial is product of these two polynomials, and you can check that it is even product of these two ideals, ideal generated by x plus 1 and ideal generated by x minus 1. Okay, so let's name it as I. So let's call this I, and let's call this J. So here I and J are comaximal. So comaximal means what? That the sum is the whole ring. Whole ring means here it is Rx. Can you see why I plus J is the whole ring? So okay, let me write, because if you take x plus 1 and if you subtract with x minus 1, you will get 2, which is belongs to I plus J, and 2 is a unit in R. 2 is a unit in Rx. So an ideal generated by an unit should be the whole ring. So I plus J is comaximal. So by Chinese remainder theorem, Rx mod I times J should be isomorphic with Rx mod I cross Rx mod J, because here I and J are maximal ideals. Right. Now what is Rx mod I? So this is basically x plus 1, and this is basically, sorry, this is not isomorphism, this is Cartesian product, x minus 1. Now can you say what these quotients are? I think you have saw this in the earlier problem solving sessions, or even in the lectures also. So can you identify this quotient and this quotient with something known? So both are actually isomorphic with R. Okay. So both, this is also R and this is also R. So recall, uh, so we have proved that Rx mod ideal generated by X is isomorphic with R, right? So how we have proved this? We have defined phi from Rx to R by evaluating by phi of fx mapping to f of 0. So for this one, okay, so I will write here. So take phi 1 from Rx to R, phi 1 of fx, you evaluate it at -1, and similarly you define phi 2 and you evaluate it at f of 1. Then you will see kernel of phi 1 is ideal generated by x plus 1, and kernel of phi 2 is ideal generated by x minus 1, and those are uh, surjective maps, so you can use the first isomorphism theorem. Kernel of phi 1 is x plus 1, kernel of phi 2 is x minus 1. So I have done one thing, just f of x goes to f of 0. So the proofs are essentially same. So you just try to imitate those proofs and see it here. So I hope up to this thing it is fine. Is it okay? So did you understand? Okay. So this quotient is actually r cross r. So now let's go back to the problem. So we have identified this quotient with r cross r. So this is just Cartesian product of two fields. Now can you say, is this an isomorphism or not? So observe that r cross r, it has no non-zero nilpotent elements, right? So every element has the form a comma b, and both a and b are real numbers. So if both a and b are non-zero, this element cannot be nilpotent, right? Because a comma b power n will be equals to a power n comma b power n. So a power, if a is non-zero, so this is non-zero. So this ring has no non-zero nilpotent element, but this one has non-zero nilpotent element, which is you take x and take the this one. If you square this, you will get x square mod x square, that is 0. Now here r cross r has no non-zero nilpotent elements, but Rx mod x square has non-zero nilpotent elements. So this cannot be isomorphic. Or the easiest thing you can do is, can you find the prime ideals of this ring or maximal ideals of this ring? So let me call this method 1. So this is method 1, which uses the Chinese remainder theorem. Let's do it by another method. So what are the prime ideals of Rx mod x square minus 1? So can you say how many prime ideals? this ring has? Or maximal ideals, at least if you can say. So ideals of this quotient are basically ideals of Rx, which contains x square minus 1. So if P is a prime ideal of Rx which contains x square minus 1, so what can you say? So this will imply x square minus 1 uh, belongs to P. So this will imply x plus 1 times x minus 1 belongs to P. But P is a prime ideal. So either x plus 1 belongs to P or x minus 1 belongs to P. Right? But ideal generated, okay, let me write. So this implies ideal generated by x plus 1 subset of P or ideal generated by x minus 1 subset of P. But ideal generated by x plus 1 is maximal because of this homomorphisms. Because the quotient is isomorphic to R and R is a field. So either x plus 1 equals to P or x minus 1 equals to P. Because P is a proper ideal and this is a maximal ideal. So by definition of maximal ideal, this ideal has to be equal to P, right? That is by definition of maximal ideal. So if P is a prime ideal that contains x square minus 1, then there are only two choices for P, right? So in this quotient, we have only two choices for prime ideals. So what are these? First one is x plus 1 mod x square minus 1 and x minus 1 mod x square minus 1. So this quotient ring has only two prime ideals. Is it okay? Do you have any doubt in this? So we are using the correspondence theorem. So this quotient has only two prime ideals. Now what about the other one? Rx mod x square. So how many prime ideals this quotient ring has? So what are the prime ideals in this quotient ring? Yes, exactly. It has only one prime ideal. So you just again use the correspondence theorem. So similarly, Rx mod x square has only one prime ideal, and which is ideal generated by x modulo ideal generated by x square. So this has two prime ideals and this has one. So these two cannot be isomorphic. So we have did it by two methods. One is correspondence theorem and one is by using the Chinese remainder theorem. So now if you have understand this well, you should do the third one. Is this isomorphic or not? Just think it for a few minutes. So, do you have any guesses that this is isomorphic or not? Yes, it has two maximal ideals. So, do you have any answer that uh, this is true or false? Any guess? So, basically, you can use the Chinese remainder theorem again. Yeah, both has same number of maximal ideals. Those are only prime ideals also. So, from that you cannot conclude anything. Yeah. So, okay, let's see. First one is Cx mod x square plus 1, right? So again, if we want to use the Chinese remainder theorem, so this is isomorphic to Cx mod uh, x plus I, ideal generated by x plus I, times ideal generated by x minus I. And these two ideals are co-maximal. Again, you can check because their sum will give you the whole ring. So by Chinese remainder theorem, this is just x plus I, and it is Cartesian product with x minus I. So up to this, it should be fine. So by Chinese remainder theorem. Now, what about these two rings? Can you identify these two rings with something known? Yeah, both isomorphic to C by the similar reason as we have done in the earlier cases. So this is C cross C. Now what about the other one? Cx mod x square minus 1. What about this? This is also Cx mod x plus 1 times x minus 1. So again you use the Chinese remainder theorem. So this is Cx mod x plus 1 cross Cx mod x minus 1. Now again use the same logic. This is isomorphic to C cross C. Both these rings are isomorphic to C cross C. So that means these two rings must be isomorphic. So this is true. So is it clear? Okay. So if you have any doubt, you just go back in the video and take a look. Still, if you have any doubt, you can come back in the next problem solving session. So you just have to use the Chinese remainder theorem and the correspondence theorem. That's the crux of these problems. Okay, so here we have talked about Cx and Rx, right? So now let's try to identify the maximal ideals of these rings. Okay, before that, the assignment 3 problem. Okay, so can you say what is the doubt? Okay, let's do that assignment 3 problem. This is maybe problem number 4. So it is that choose the correct answers. The number of maximal ideals in the quotient ring is, so it is true or false. The number of, okay, you are saying this one or something else? You are saying assignment 3 option 3. Okay, not this one. The number of prime ideals in the quotient ring. Number of prime ideals in Z mod 2025 Z is 2. So are you talking about this one or something else? So we're talking about which one? Problem 1. Okay, problem 1 option 3. Okay, sorry. Problem 1 option 3. sorry. Let R and S be rings, ring homomorphism. Choose the correct statement. ZXY be the polynomial ring, the quotient ring. Okay, let me write down it here. So it is also true and false type. So R is your Z x1 x2 and S is your quotient ring R. Okay, let me write out clearly. So it is just Z x1 x2 modulo x1 comma x2 and phi from R to S, the natural surjection, natural homomorphism. So for every ideal I, phi of I is an ideal of S. So for every ideal I of R, phi of I is an ideal of S. So it is true or false, right? So what do you think? It is true or false? So what is your doubt in this question? So the problem is if you take an ideal of R and if you take the image of I via phi, then it remains an ideal or not. So this is true, right? Because phi is surjective. We know phi is onto. So we need to prove, we need to show phi of I is an ideal of S, right? So you just prove that two property of ideal. One is subgroup and one is that absorption property. So for A comma B belongs to phi of I, A minus B belongs to phi of I. This is the first one. Second one is A belongs to phi of I and X belongs to S. X A must belongs to S. So can you prove this too? So A and B belongs to phi of I. That implies there exists A prime B prime belongs to I such that uh, phi of A prime equals to A and phi of B prime is equals to B, right? By the definition. So A prime minus B prime is in I because I is in ideal. So that will imply phi of A prime minus B prime, which is A minus B, is in phi of I. And if A belongs to phi of I and let's say X belongs to S, this implies phi of A prime is equals to A for some A in I, right? Now uh, uh, and also phi of some X prime is equals to X for some X is in R because phi is onto. So X prime A prime belongs to I because I is an ideal. So that its image phi of X prime A prime, which is equals to XA, must be in phi of I. So is it okay? So there is no role of this particular ring. It is true for any ideals in R. कैसे होते हैं? Ideals in R. This is a polynomial ring in two variable. You can uh, generate it by any. You can take any polynomial and generate an ideal. You cannot say any particular thing because this is not an principal ideal domain. This is just a ring, and that does not matter here. It is this result is true for any surjective homomorphism, and since it is a natural homomorphism, so it is a surjective homomorphism. Yeah, okay. Okay, so if you understand this, so let's move on to the next problem. So let's try to see the maximal ideals of Cx and Rx. That is something interesting. So problem number 5. It is about maximal ideals in Cx. Okay, so how the maximal ideals in Cx looks like. So first of all, so first point is every ideal in Cx is principal ideal, right? That is something we have saw in the lectures. So every ideal is generated by single element because uh, C is a field. So if you take a polynomial ring over a field, then that is a principal ideal domain. So you will see this in the next lectures, that Cx is a principal ideal domain. So if, and also we have saw, if I equals to generated by fx is an ideal, this is maximal if and only if fx is an irreducible element, right? These two things has been done in the lectures. I hope you can recall it. So first of all, every ideal is principal ideal, so it has this form. So we need to check when an ideal of this form is maximum. So we need to check when a polynomial is irreducible. So can you guess when a polynomial in Cx is irreducible? Means it cannot be, okay, an element, let's say A, is irreducible if it cannot be written as product of two other non-zero non-unit elements. Cannot be written as A equals to some B times C, where B comma C are some non-zero non-unit elements. So in case of polynomials, you cannot factor this polynomial into smaller polynomials. Okay, so this is the definition of irreducible element. I hope you have saw this in the lectures. So a polynomial let's say fx belongs to cx is irreducible if and only if degree of fx is equals to 1. So do you agree with this, or you have some problem with this statement? So first of all, uh, fx cannot be unit, and not zero also, non-zero, non-unit, because fx is irreducible implies fx is non-zero, non-unit by definition. So that means degree of fx is at least 1, right? Because non-zero, non-unit, that means it cannot be constant. So it cannot be constant, so that means degree of fx must be 1. So it is exactly 1. So if degree is, if degree of fx is strictly greater than 1, then, because we know that cx, every polynomial with constant coefficient, complex coefficients, if it is a non-constant polynomial, then it has a root. Then if alpha belongs to c is a root of f, then fx can be written as x minus alpha times some gx, right? So then it can be written as product of non-zero, non-unit elements. So then fx becomes reducible. So this is not true. So degree of fx be 1. So yeah. So this is because every non-constant polynomial in Cx has a root. So this is known as fundamental theorem of algebra. I think you have saw this. So that is very important here. We are using that. So f is irreducible if and only if degree of fx is 1. So is it fine up to this? So I equals to ideal generated by fx is maximal in Cx if and only if fx is equal to some x minus alpha. Means it has degree 1, so it must be of this form for some alpha belongs to C. Did you got this? So first of all, uh, we need to find the maximal ideals of Cx. How the maximal ideals looks like. Every ideal is principal, so maximal ideals are also principal. So maximal ideal, uh, let's say I is a maximal ideal generated by fx. So we need to describe this fx. Now we know I generated by fx is maximal if and only if that fx is an irreducible element, right? So we need to determine what are the irreducible elements in Cx. Okay, so then we are claiming the irreducible elements in Cx are only degree 1 polynomials. So degree 1 polynomials are always irreducible because they cannot be factored out into non-zero, non-unit elements. And conversely, if f is irreducible, then by definition it has to be non-zero, non-unit. So that means it cannot be a constant polynomial. So its degree is at least 1. Now if its degree is bigger than 1, so uh, it has more than 1 roots. So just take one root and factor it out. So then you can find a factorization into non-zero non-unit elements. So then it will no longer a irreducible element. That means degree of fx has to be 1. So I equals to generated by fx is maximal if and only if fx equals to x minus alpha. Hence it is a degree 1 polynomial. So is it fine? Okay. So that means for every complex number alpha, you will get a 1 degree polynomial, and that will give you a maximal ideal. So from this, we are saying you take maximal ideals in Cx. You just take this set of maximal ideals, and here you take points in C or the complex number. So these two sets are in one-on correspondence. So yes, I'm saying we have a bijective correspondence between the following two sets. So what is the mapping here? So if you take an ideal, let's say M, ideal generated by x minus alpha, you send it to the point alpha, and if you have a point here, let's say beta, you send it to the maximal ideal again x minus beta. So then these two functions, one is this one, let's say this is phi, let's say this is psi. So then these two functions are uh, inverses of each other. Means compositions will give you the identity. So that will give you the one-on correspondence between these two sets. So just remember this thing. It is not that much difficult. You just have to realize this. So this thing is a part of one more celebrated theorem. So I will just state that. Uh, I'm not going to the proof. So I've done problem number 5, 6. So that is known as Hilbert Nullstellensatz. So this theorem says that uh, the maximal ideals of the polynomial ring C x1 up to xn, means the multivariable polynomial ring, are in bijective correspondence with the points in C power n. So in our case, we have taken just one variable. So in that case, it will be a bijective correspondence with points in C. But it is true in multivariable also. So this is a very basic part of Nullstellensatz. I am not written the complete one, but this is something you can take it as information. So we have saw the maximal ideals of the polynomial ring C x1 up to xn. Okay. Now let's see the maximal ideals of Rx. Okay, let me write down the question itself. So prove that the set of all maximal ideals of Rx. So the set of all maximal ideals of Rx are in 1-1 correspondence uh, with the points in the upper half plane. Okay, so upper half plane means if you just take the plane R2 or C, it is the just this upper part, means it is the just positive y-axis. Means those points whose y coordinate is non-negative, so including the x-axis. Okay, so I hope you have understood this problem. So we need to prove the set of all maximal ideals of Rx is in 1-1 correspondence with the points in the upper half plane. In case of it is Cx, then it is in 1-1 correspondence with the whole complex plane. But in case of Rx, it is just with the upper half part. So for this, let's try to uh, describe the maximal ideals of Rx first. So as we have done in the case of Cx, let's see what are the maximal ideals of Rx. So in Rx, also Rx also a PID, right? So okay, let me write clearly. Now let I be a maximal ideal of Rx. I have taken maximal ideal of Rx. So we need to describe the ideal I. So then I is generated by some fx. and this fx has to be irreducible because of the same reason as we have seen in the case of cx. For some irreducible polynomial fx in. So our task is to describe the irreducible polynomials of Rx. So can you give some description of that, or can you guess at least what polynomials are irreducible in Rx? Which polynomials in Rx uh, cannot be factored into smaller polynomials, or at least can you say about the degree of those polynomials? So first of all, degree 1 polynomials are always irreducible. Okay. So the question is, uh, are there any more? So fx belongs to Rx is irreducible if and only if degree of fx polynomials with roots only in C are also irreducible. Yes, yes, you are correct. But can you say about the degree of those polynomials? So fx belongs to Rx is irreducible if and only if degree of fx is 1 or 2. There cannot be other. So why cannot be other polynomials which are irreducible? So let fx belongs to Rx such that degree of fx is greater than 2, right? Then I will show fx cannot be irreducible. So if degree of fx is odd, then we know that odd degree polynomials has always a real root because complex roots occurs in pairs. So odd degree polynomials cannot be odd degree, and degree is not 1. Those polynomials cannot be irreducible because those has factors. So if degree of fx is 3, then f has a real root. So f cannot be irreducible. Now what about degree 4? So if degree of fx is 4, then what can you say? So if degree of fx is 4, then it may not have real roots, right? So let me, so case 1, if f has real root, then it is reducible, right? Now case 2, f has no real root, then what can you say? So all roots of f are complex numbers. So then f has two pairs of complex roots, right? And complex roots occur in pairs, means uh, both of them are conjugate of each other. So let's say alpha 1 plus minus I beta 1 and alpha 2 plus minus I beta 2. Okay, so these are four roots of f. So then you can check that f can be factored into 2 degree 2 polynomials. Then check that f, okay, note that. Then note that f can be factored as 2 degree 2 polynomials. So this is something, you just check it. You just take a real polynomial of degree 2 whose root are only these two complex numbers. Then you can check that coefficients will be real number. So f is reducible. So it is sufficient to look for only degree 3 and degree 4, because all our higher degrees will come from this. So if degree is greater than 2, then f cannot be irreducible. So is it okay? Okay, fine. So f is irreducible if and only if degree of f is 1 or 2. So in case it has degree 2, then it has no real root. The roots are complex conjugates. So ideal generated by fx is maximal in Rx if and only if degree of fx is 1 or degree of fx is 2 and if f has complex conjugate roots. If, let me write more clearly, f has a pair of complex conjugate roots. Right. Now, if you draw the complex plane, so two roots which are conjugate. So conjugate root means it is just the reflection of the x-axis. So if one root lies in upper part, then its conjugate must be lie in the lower part, right? Or vice versa. So that is the meaning of complex conjugate. So you just take, okay, take a maximal ideal I equals to generated by fx in Rx, then we can associate a complex number with this, right? How we will associate that? Then we can associate a complex number lies in the upper half plane. So as follows. So if degree of fx is 1, so fx is just x minus a for some a belongs to R. So you just attached a. So attach a with f of x. Now if degree of fx is 2, then f has roots alpha plus minus I beta, in which one of alpha plus minus I beta must be lie in the upper half plane, right? Because both are complex conjugate, so one of them must be lie in the upper half plane. So attach that root. So this correspondence will give the proof of our statement. So that is the one-on correspondence which we are looking for. So here you have maximal ideals in Rx, and here you have points in the upper half plane. Both these sets are in one-on correspondence. So did you got at least the sketch? Because we need to explicitly give the function which gives the bijection. That will come from this attachment of these roots. So that I have not written rigorously, but it can be understood. Okay. So I hope so. In particular, you can take the, so one of these two roots must in the upper half plane. So in that case, the other one should be in the lower half plane. So this is also in correspondence with the lower half plane also. So that is also true. Points in the lower half plane. So either you take the root in the upper half plane or in the root in the lower half plane, and do it for the all maximal ideals. Then you will get this correspondence. So is it fine? Okay. So if it is okay, so let's do one more The next one is I feel very interesting. So problem number 8. So prove that mm, the ring Zi modulo I minus 2 is a field. So we need to prove that this quotient ring is a field, or this ideal is a maximal ideal. So both are same. So how we will do it? So there are several ways of doing it. Just by looking the elements of the quotient can also fine, is also fine. But we will do explicitly. So first of all, we will try to see this quotient ring with means we will try to uh, identify this quotient ring with something known. Okay, how to do that one? So now observe that z of I is actually isomorphic to zx mod x square plus 1, right? So this is something we are doing for several problems, from several problems. So how this is isomorphic? So this is by, so you take f from zx to z of I, and you send f of px to p of I. Then you look at the kernel. Kernel will be ideally generated by x square plus 1. Then by first isomorphism theorem, you will get this isomorphism. So, uh, so here we have zx, and here we are taking z of I. So here we are killing the ideal x square plus 1. Then we are getting this quotient z of I, and after that we are taking this quotient z of I mod I minus 2. So this is a quotient of z of I. So it is a quotient of zx mod x square plus 1. So z of I mod I minus 2 is a quotient of z of I, which is isomorphic to zx mod x square plus 1. Now, uh, what is the image of x here in z of I? So here x is mapping to I, right? So we are identifying x with this element I. So same thing we can do here. So I want to say that if we take this ideal and quotient it out here, how it will be look like. So the ideal I minus 2 can be identified with, so we are identifying I with x. So you just replace I with x. with x minus 2 means in zx mod x square plus 1. So that means z of I mod I minus 2 is isomorphic with zx mod x square plus 1 uh, comma x minus 2. So ideal generated by these two elements. Right? Now, so we are going backwards actually. So from this quotient, we have get this quotient. We are going backwards. Now we need to identify this quotient. So if you take this quotient and you first kill x square plus 1, you will get this one. So what about the other way? So if we first kill x minus 2, then what we will get? So look at this diagram. So from zx, by killing x square plus 1, we are getting this quotient. So we can kill the this x minus 2 also. So if we kill x minus 2, so then we will get z, right? So I am saying that this is yeah, because zx mod x minus 2 means we are killing x minus 2. So this is isomorphic with z. So here what we are identifying x. So here we are sending px to p of 2. So that means x is going to 2. So now we want to go here. So actually not this quotient. So what will be this quotient? So kill I minus 2. So if we first kill x minus 2, so x is replacing with 2, right? Then how this ideal will look like? So in zx mod x minus 2, the ideal x square plus 1 is basically 5 because of this reason. Because we are identifying x with 2. So now we need to kill it by 5. So here you just kill 5. Means you just go modulo by 5. So that you will get z mod 5z. So zi mod I minus 2 is basically z mod 5z. So what we have done is we have zi mod I minus 2, zi mod I minus 2. Then we have identified this with this quotient ring. Now we are killing x minus 2 first, then we are killing x square plus 1. And you can do the other one also. You can kill x square plus 1 and kill x minus 2 in the second. But that will be complicated. So we are just doing the reverse thing. So if we kill x square plus 1 first, then we will get z of I and kill x minus 2 means that will be I minus 2. But from that, identify z mod 5z is difficult. So we are killing x minus 2 first. Then we are identifying x square plus 1 with ideal generated by 5. And we are killing it. And z modulo 5z is the ultimate uh, answer. And this is a field. So did you understand the idea? So I will do one more of this type. So if you still not got the idea, then I hope you got it from the next one. So do you have any doubt in this, or can go to the next one? Okay, so let's quickly go to the next one. I hope you will be you will got more clarity from that. So prove that the ideal I generated by 2x minus 3 comma okay x minus 10 is a maximal ideal of zx, right? So we need to prove this ideal is maximal ideal of zx, ideal generated by 2x minus 3 comma x minus 10. So we need to prove that this quotient, so we will prove zx mod 2x minus 3 comma x minus 10 is a field. So to prove that it is a field, we will identify this ring with something known. So again, you have two polynomials. So you can kill by 2x minus 3 first, and you can kill by x minus 10 first. So you need to check which one is easier. So here we have zx. So let's kill it by x minus 10. That means we are going modulo x minus 10. So if we uh, take zx and go modulo x minus 10, what we will get? We will get just z. So if we kill x minus 10, we will get z, right? So now zx mod x minus 10 is isomorphic with z. And here we are identifying x with 10. Okay, let me write the complete thing. This is by f of x going to f of 10. So x going to 10, right? Now let's see what will be the image of this ideal in this zx mod x minus 10. So 2x minus 3 becomes 2 times 10 minus 3, so equals to 17. So it is ideal generated by 17 in z. So you just need to kill it by 17. So then you will get z mod 17z. So that is the isomorphism. So zx mod 2x minus 13 comma x minus 10 is basically uh, z mod 17z. So you can do the other thing also. I mean, so you can kill it by 2x minus 3 also, but after killing by 2x minus 3, here what you will get, that I don't know, that is not easy to find. So we have killed by x minus 10 first. So this quotient is isomorphic to Z mod 17Z, and that is a field. So 2x minus 13 and x minus 10 is a maximal ideal. So is it okay? Yeah. So you can write a rigorous proof without doing this also. So for that, what you need to do is, so you just directly define from Zx to Z the characteristic map, where okay, the other way, from Z to Zx, you just define the map n goes to okay, Zx mod that ideal I, n goes to n plus I, the quotient. Then you prove that, let's say it is phi, then you prove that kernel phi is 17Z. So that is also something you can do, that is also easier, but this method is will give you the flavor of this problem. Okay, so we have done lots of things on correspondence theorem and maximal ideals of this thing. So the last thing is Noetherian rings. So let's do one more problem. So Noetherian ring means every ideal is finitely generated. So this is a true false type question. Let's say Z root minus 2. You take this ring. So the ring Z root minus 2 is a Noetherian ring. So it is true or false. So think it for a few seconds. So what do you think? It is Noetherian or not? So we have saw the Hilbert basis theorem, right? So Hilbert basis theorem says if R is Noetherian, that will imply the polynomial ring Rx is also Noetherian. Right? That is one thing we have saw. And second one is if R is Noetherian ring, then R mod I is also Noetherian. So we have solved this result also in the lectures. So using these two, can you solve this problem? Means this Z root 2 is Noetherian or not? Yeah, any guesses? It is true or false? Okay. So, note, I think it is false. Okay. So, why do you think that it is false? So, can you identify any ideal which is not finitely generated, or by any ascending chain which is not of finite length, means which does not stabilize? Okay, so let's see this. So first note that this z root minus 2 is basically isomorphic with zx mod x square plus 2. Why? So you just take f from zx to z root minus 2 by f of px goes to p of root minus 2. Then use the first isomorphism theorem. Okay. Now zx is Noetherian by Hilbert basis theorem. Since z is Noetherian. Z is Noetherian because every ideal is principal. So every ideal is finitely generated. So Z is Noetherian. So Zx is Noetherian. So thus its quotient is also Noetherian. So Z root 2 is Noetherian. So this is true. Okay. So I hope you have understood this proof. Yeah. Okay. Okay. So do you have any other doubts? Okay. So if no more doubt, then we will close this session here. Yeah. Okay.